Lunar Network SIG, and we do in the form of a weekly hangout. And today's event ID is 140610, and the co-host Mike Riley would do the presentation today. We will follow it with a discussion after that. And good morning, Michael. Go ahead, take it away.
Very good. Yeah, this is a little earlier than our usual time, but we have some other things that we have to take care of. So I'm glad to be able to talk with you today. We're going to talk a little bit about some initial thoughts about the ground segment. Abraham, do you see the ground segment slide?
Yes, the slide is coming okay. Go ahead.
All right. So this is an exploration just to get some of our first ideas out there. We're drilling down into the different subtopics in our Deep Space Information Systems Special Interest Group. We've talked about the space segment before. We've talked a little bit about some support software and modeling and simulation before, about how you actually come up with architectures. And today we're going to take a look at some of what's possible for the ground segment. Once again, the vision of the lunar networks is to provide an analog of some of the service capabilities that we have here on the Earth, except extended to the lunar surface through a lunar cloud which lives on top of spacecraft and rovers operating in cislunar space, both in orbit and on the ground itself. The infrastructure that supports that is an extension of the ground, the infrastructure, the data infrastructure that we have in low Earth orbit and on the ground as well. So we take maximum opportunity of the advances in telecommunications and computing that we have on the Earth, and also our improved capabilities in space, both with conventional spacecraft like LADEE and Lunar Reconnaissance Orbiter and things of that nature, as well as upcoming spacecraft that are being planned to be sent to the moon or the cislunar environment in recent years, or I shouldn't say recent, but will be shortly upcoming. The focus today is to look at the ground segment section of that, and we're taking an operational viewpoint. From an operational viewpoint, the ground segment is traditionally involved with things like telecommunications, ranging, and tracking. So the ground stations are a big important part of that. Also there's a distinction, say, with ground terminals, where you have both uplink and downlink between the spacecraft and the ground. One thing to notice is that the ground stations are a link from the Earth up to the spacecraft, but you also have to get that data from your ground station to the location where it's actually used by the different stakeholders, the spacecraft operators, the engineers, the scientists, and other people who use these spacecraft operations. Now, one interesting thing that we have going on with the advent of reliable assets in space with our space-based communications, assets in low Earth orbit, geosynchronous orbit, even specialized communication satellites like the Molnias that are used for higher latitudes, and TDRS, which provides 24/7 access to the low Earth orbit environment. What counts as ground anymore? If we rely on these Earth orbital assets as well as GPS, you don't have to rely just on things that are on the planet, and so you can start to talk about extending the networks out into space as well. Another item that comes up is that space is inherently international, and since we are very interested in pushing forward commercial and private uses of space, some of the issues that that come up with, say, state-based uses of space don't necessarily apply. So you can come up with different solutions than, say, a government agency like NASA. You can put together international cooperations or cooperatives to take advantage of some of the flexibility that you get if you're not tied into a government-based approach. But with regard to the ground segment, getting back to that, the things that happen on the ground control and operations, mission planning, and also getting the data out to the people who are actually going to use it to make decisions or to get some other sort of value from the data that is acquired or the operations that are done in space. All those are strongly connected to the ground segment. Now, there's an evolutionary theme that's working here, and that is that near Earth space is growing outward. For example, NASA's first communication and tracking system is the Space Tracking and Data Network, operated by Goddard Space Flight Center, and it has 11 terminals and stations around the globe. And this is the one that NASA put together to talk to its spacecraft, starting in the early 1960s. This is essentially an entirely ground-based system with telecommunications cables, and it's been upgraded over the years to take advantage of other kinds of communications technologies. But this is being phased out in favor of the geosynchronous orbit-based tracking and data relay satellite system, which currently has 8 very highly capable spacecraft that can provide all sorts of real-time and high bandwidth communications. One thing to consider is that the spin-offs from the space program are spinning back into the space program. A lot of the problems that the early space program encountered and the solutions they came up with over several years really got the balls rolling. And those technologies, those solutions were picked up by the larger commercial and technology users beyond just aerospace, and they've really blossomed out there. For example, just embedded computing and digital signal processing have made enormous strides in everything from, say, digital imagery to the handheld radios that we call cell phones, and with massive amounts of data and computing power on them. This has given rise to a wide range of advances for commercial off-the-shelf and terrestrial use that are now coming back to the space program and enabling things like the Cube spacecraft. And there's just a whole list of things that come in here. One interesting aspect is that just putting together the spacecraft, the margins are so thin in aerospace that systems engineering and quality assurance are extremely important and big deals. And that's one of the main things that I think that one of the unsung success stories of the aerospace program is that they did make very big strides in systems engineering and quality assurance, particularly in the late 1960s. And early 1970s. So some of that knowledge and background was paid for with a pretty high price. But that capability to design and engineer systems has paid off dividends throughout the engineering and technology world. And this has led to things like the advances in software engineering and in hardware. So what you have is you have the basic R&D, which has been supported or started to solve aerospace problems, being amplified by things that happen in terrestrial or real-world use that you and I use on a daily basis and pretty much take for granted right now. So, bringing these back in, what are some examples of some of the things that have been enabled by this advance of technology and the wave of technology coming back to aerospace problems? Consider, for example, GENSO, the Global Educational Network for Satellite Operations. It's a European supported effort with an international partnership. Wide range of parties, particularly educational and other and amateur radio supporters as well. It is a satellite operations network consisting of a large number of control centers and ground stations that provide access to spacecraft, particularly educational spacecraft, which are operated by member institutions and some others. Some of the things that go into this that have enabled this particular this network of spacecraft communications terminals and stations, it's built on the international on the internet. It uses software standards and under, again, ESA, with some ESA support and guidance. It's Java-based software, so it really lowers the cost of entry into working with spacecraft data and communicating with different communicating with the spacecraft as well. Some of those are pretty advanced operations, 24/7 operations, actually sending up commands to the spacecraft and bringing down data and making it useful for students and others throughout the world. That's one example of something that has been enabled by the advanced and ground-based networking and computing and communications technologies. Another example is, well, what do you consider to be ground? One of the things that we're talking about with the LunarCubes and opening up the cislunar environment is that well, the lunar surface, the communications technologies that work between, say, low Earth orbit and the Earth's planetary surface, well, you'll have some analogous or very similar technologies for communications between lunar orbit and the lunar surface as well. So for just a quick example, take LEO to ground communications, the FunCube effort with the educational satellite. There you have a little dongle which you connect to your computer, run it out to an antenna, and you can receive real-time telemetry from an orbital asset. Okay, so this is an amateur effort associated with some educational institutions as well. You can go out and spend a little bit of money and start to listen to data coming off of a real spacecraft. So it's really lowered the boundary and the cost of entry to being able to work with and use space assets. If you take a look at some of the ground segments, direct communication to Earth from a deep space cube spacecraft. Right now, you already have the deep space network. So if you have your transceiver on board your cube spacecraft, which is set up for JPL based communication, and JPL is putting together such a transceiver, you can communicate with the deep space network. Other options, you have radio astronomical assets for listening in to things going on in cislunar space. For example, we've talked with SETI to talk about listening to and communicating with spacecraft. Also, very large array. Perhaps we can get involved with their effort and get some time with them to listen to some of our cube spacecraft. You can also pull in, say, the amateur radio enthusiasts and also other educational institutions. And I have another example of an educational institution that has some pretty good experience and capabilities working with cube spacecraft and is interested in deep space as well. Another aspect is the indirect communications to Earth via a spacecraft, a more conventional spacecraft, which is already in lunar orbit. For example, Astrobotic Technology and Moon Express. These guys are planning on sending things to the moon with more conventional transceiver technology being used. With the advance in electronics and radio communications, we can start to put up mission architectures where you have your cube-based lunar rover or even spacecraft operating in the moon, which communicates and uses these more conventional assets as a communication relay. take advantage of what you might call a big pipe, communications pipe to Earth. Some examples continued about different ground segment capabilities, and these are just a small fraction of what's going on out there. If you look at things that are happening and being made available via open source, for example, you have the General Mission Analysis tool, which is put together at Goddard that can help you plan your mission. Mission control technologies, again, that was developed out at Ames, so those are perhaps some capabilities that you can use to actually help control your system. An example of a CubeSat control operation, which has gotten significant support from funding agencies and the university, is the Mission Operations Center down at Morehead State University. So you can actually start to put together operations centers, even tie them together and make them part of, for example, the international network that we talked about before. So the barriers to access, the cost of entry to getting involved with spacecraft is as low, I think, as it's ever been, and some exciting things can happen. Another example of using some legacy equipment is a repurposed 18-meter radio dish out at Wallops Island, which I understand, reading a news article about it, they actually have components from an old battleship. The gears that turn the thing around are actually salvaged from a real battleship. So I found that to be interesting. But the main point is that you have legacy equipment which can be repurposed and be used for these new CubeSat enabled missions. And again, speaking to the democratization of access to space and the provision of data to end users or stakeholders, you have an example of, say, the FunCube Data Archive. You can go to that website and download real-time or near real-time or archived data from the FunCube spacecraft and take a look at how it's behaving and take a look at what sensors are on board. You can learn something about the engineering data that comes off of a spacecraft. So that's an example of one aspect of the ground segment, which is to process the data and make it available to end users, as well as to the folks who actually run the spacecraft itself. One item that we touched on is that really the technologies that you're talking about link, say, a planetary surface to communications assets which could be in orbit. And that planetary surface could be pretty much anywhere in the solar system, particularly if you have a conventional communications node or even an advanced one, for example, the optical links that are pictured in this notional architecture. I believe this is from Cornell University that NASA is supporting. The notion here is that you can use your Cube spacecraft-enabled specialized mission segment, for example, a little CubeSat-enabled rover that communicates with something that is nearby or in orbit and uses that as a relay to get the information back to Earth and take advantage of the ground segment. So what I'm trying to get across with this particular slide is that we need to expand our notion of the ground segment, not just the terrestrial ground segment, but also the ground segment that you have on perhaps other planetary bodies as well, as you start to implement networks on the planetary surfaces and the orbital environments of those planets, and linking them together with your long-range, long-haul communications. So in summary, there's a wide range of legacy assets and tools that are available. These include hardware, infrastructure, for example, the Deep Space Network from JPL. All of these assets, tools, and equipment provide a baseline of capability that we can use as a foundation to build new capabilities and get things going. New technologies, for example, the Cube spacecraft technology, itself are enabling new capabilities and lowering the cost of entry and reducing the risk, the cost risk associated with trying new things. And that's great for innovation. Parts of the ground segment that we talked about earlier, we talked about telemetry and operations, data processing and providing the data that you get from your deployed assets, providing that data to the end users, engineers, scientists, and others who are interested in using that data. And again, the fundamental point is that's lowering the cost of access and increasing the potentials and opportunity for participation in developing and exploring space. So the ground segment is an important part of the overall picture. There's a lot that already exists with the ground segment, and there's a lot of new capabilities coming online that will allow new players to enter into the field of working with and communicating with, operating these remote spacecraft. That concludes my presentation. And so now, if you have any questions, or that opens the discussion. And you're on mute, Abraham.
Yes, Michael. That was quite an insightful presentation, and thank you for that.
Oh.
And this is more or less to kind of continue with our discussion we had earlier. And what are the few things that come across to you, like been seen in terms of deep space information system?
Well, one of the main points about what I talked about today with regard to the deep space information systems is that all of this sort of sits underneath the information systems that you build on top of that. So I did not go into, for example, the delayed tolerant networking that would be an important part of this. I also didn't talk about the possibility of making a lot of what I was discussing today transparent to an end user. For example, we take for granted the engineering that goes into the internet that makes it that hides a lot of the detailed complications, the different gateways going through the different protocols. We just type some things into a form, click send, and the service is provided to us. So most of what I was talking about today is at something of somewhat of a lower level than where you would actually like to get to, where you start to have the different assets interacting with each other and providing services to each other, perhaps even constructing those services by combining the capabilities of different space-based assets to actually solve individual problems which we submit to the network.
Very good. And on the same page that you're showing right now, these assets which are already in space, how would these be cataloged or made visible to the operations center, or at some level they would be a node element or a entry point or some entity being able to be recognized within the lunar network that we're talking about, or those assets may from time to time may choose not to be part of the network. You have some notion of how that will exist in our system eventually?
Well, the first item is that there's a lot that's still notional on this particular slide. So there's a bunch of assets that are projected to exist on this particular spacecraft, on this particular slide, that do not yet exist. The the second aspect that you're talking about, assets coming into play, going out of play, that's one of the fundamental interesting things that you have about space-based networks, that you have a little bit of, or that you have to some degree with the Earth-based assets, but not nearly as much. For example, a spacecraft goes out of view of a particular communications link, and you have to, in order to maintain, say, the responsiveness of your network, you have to have another spacecraft coming into play and then handing that trade-off from one to another. Those are some things that you have to, that we try to engineer around on Earth-based or terrestrial networks, or just connect a cable between them. You can't do that with the spacecraft assets. The delay-tolerant network is one way to address some of what you're talking about. Another item is, one of the aspects of what you're talking about is essentially resource discovery. So there's a dynamic nature in that, and there's also a programmatic nature. Some of that is going to have to be taken care of by smarts that are built onto the spacecraft itself. So, for example, there's the ring concept, ring network concept that was, I believe, developed by a group out at JPL, in which the individual nodes essentially keep ephemerides of the different assets so that they can predict when something is going to be in view and where it's going to be, so that it can construct essentially a dynamic routing table to decide where it should send a particular communications, so that when that spacecraft picks up its packets and flies around the planet to the other side as it goes through its orbit, you send the right packets to the right spacecraft that then carries it around to a place where it can get another downlink. So you can actually connect different, say, ground-based networks through, essentially manually carrying it from one place to another by spacecraft. So that you have to have some fairly capable smarts which understand how to connect a dynamic route through an ever-changing network of, in that case, orbital assets. So you have that dynamic sort of route planning that you're going to have, particularly if you have a heterogeneous network of spacecraft which are providing, I don't want to say ad hoc connections, but you want to synthesize a route based on an ever-changing network of communication nodes. An interesting aspect of that is that it would be good to have some coordination ahead of time between different spacecraft. For example, India is sending things to the moon, China is sending things to the moon, ESA and NASA and Russia. It'd be good to have some coordination ahead of time so that we could actually use these spacecraft, particularly in their follow-on missions after they complete their primary missions, to use them as communications relays to provide better communications and perhaps some position or navigation information as well. It'd be good to have some prior discussions to coordinate that. Otherwise you'll be going backwards and trying to synthesize your communications networks after the fact, and just dealing with whatever the guys put together to solve their individual engineering problems.
Excellent. That's a very good point. So essentially, building a small capability like a built-in router It's not that difficult to accommodate in most of the spacecraft, or at least the future ones that's likely to go. You know, so your point is very valid. But how would we either incentivize or declare a set of um, uh, uh, structures which will allow eventually to kind of um, join these type of dynamic network situation?
Well, I think what's going to happen is that for the different players and for the different end users and stakeholders, you're going to have to convince them that the working together will provide something that is of greater value than just the individual's sum of its parts. So that working together, you get something like a web effect, so that you have a much enhanced capability, and you get much greater value. So it's a multiplier instead of just the sum of the different values. Some things that you might get from that, some things that come off uh, just through the top of my head would be perhaps more reliable and more responsive communications would be one. Sharing data from different instruments to synthesize, essentially to provide a synthetic instrument, that data that could be combined to give you a better understanding of, say, a particular problem or particular scientific need on the moon. So those are some just from rough ideas, and I know that Russell has some other ideas. For example, in providing increased bandwidth and more communication opportunities, lower communication latencies for things that you actually put on the moon. So if you can tie your different lunar assets into a network, you could get a much higher payoff, and that's what you're going to have to convince the different stakeholders, that by working together they'll get a much greater a system that provides a much greater value than you would get just from each individual node running its own program and providing value through the stovepipes.
Yes, agree, absolutely. So that kind of lead us into the future topics that we should be handling. So, off your top of the head, you have some of the topics that is relevant in these directions?
Well, I think the next layer of detail, in particular for the ground segment, would be to say, look at some of the things that people are doing for me, autonomous operations is always a big issue. If you're going to have something out in cislunar space, you're going to need something that is responsive. You're going to have to automate the inter-spacecraft communications, for example, from a ground-based asset up to something that's going overboard. That smart sort of dynamic routing, that's something that is going to have to be taken care of and handled, because if you're talking about a dozen or a few dozen or a couple hundred of communication nodes going around in cislunar space, you want to make sure that again, the cost of running that entire network, can't be much more than the cost of running a single conventional mission now. So being able to reduce the cost of operations, being able to democratize, being able to take advantage of new players, those are some things that we should be taking a look at.
Great. Okay. So while we are on the subject, I would like to just add a couple of our notes in the same direction. Okay, you see, I'm see if I can.
I have to say, it looks like Abraham just dropped out. Hope he can log back on. So in any event, the purpose of our discussions... Hello, Abraham. I have you on Skype.
Yeah. Oh, current call. Yeah, I was trying to share my screen, and suddenly the whole thing seemed to have quit.
I think that I don't know if you're being picked up by Google Hangout or not, but I can hear you fine.
No, right now I don't see the Google Hangout anywhere. Like, I was trying to share my screen so we can kind of share notes.
Well, guess what?
Oh.
I have you on Skype. The Google Hangout is still going on.
Oh.
And you're talking online.
Oh.
And we're still live. I don't know if you can reconnect to the Google Hangout without killing it, but I think it's still going on. Perhaps it's a zombie process.
Okay, so I'm going to kill the Chrome browser, so at least that goes away. Okay.
Well, okay, you can. One thing you could do is that maybe you could share your screen via Skype, and then maybe I could rebroadcast that onto the Hangout.
No, in my screen, the whole Hangout is gone.
Yes, but what I mean is that I can see. I'm still there. Well, and I
okay.
could.
Let's convert this into a debug session. It's
okay.
Sorry, viewers. Okay.
Okay. Very good.
Screen share, and I'm sharing this one. Okay. Do you see that? Do you see
oh,
the
yes.
screen?
Yes, I see your screen.
Okay. Now what happened to Google? Now that's the screen I had. Suddenly it kind of went on somewhere else.
Yeah, I couldn't tell you what happened. I can share your screen with our Hangout if you like, and we can continue the discussion.
All right. We'll just try that. Okay. And I want to kind of probably share the other screen I wanted to. That is conversation, screen or window. Okay. This is the screen I wanted to share. And
I have global zoning user community.
yes. So what I was kind of alluding is some of the next few things that we would like to do would be to start defining in terms of the deep space information system, all the elements that make the information system in that context. So there are multiple sides we have to kind of start. One is the user community. Somehow define a structure where the providers are kind of listed with their capability mapped somewhere. Consumers, where they kind of what the information is being consumed. Various types of administrators that are required and require access and authentication processes associated with that, and various stakeholders who are kind of getting in it. Okay, and remember the three regions that has to operate. So there may be local code or certain boundary conditions, or even the currency issues that may be handled differently. Then we also kind of talked about various software stack, and this is just a tiny bit of the